There are two immensely profound questions in cosmology that touch on both scientific and philosophical ideas in a most unique way. In this video, we explore a mystery even bigger and older than the universe itself, the mystery of what existed before the Big Bang. It's a question that has kept scientists and dreamers like us awake at night. What preceded our origin story? This leads us to a tantalizing conundrum that asks the second question: what is nothing? A quick history. The Big Bang Theory isn't just a TV show. It's the leading explanation for how our universe began. This idea has been around since the early 20th century, gaining steam when Edwin Hubble observed that galaxies were moving away from each other, hinting at a universal expansion. Hubble's hypothesis began to gain traction with the discovery of cosmic microwave background, CMBR, and redshift of galaxies. These are like footprints left behind by the Big Bang, giving us a sign of what went before. Cosmic microwave background radiation, CMBR. Now, onto the juicy stuff, evidence. First up is CMBR. CMBR is the afterglow of the Big Bang. This faint light fills up the whole universe. Picture this. You've had a roaring campfire, but now it's just smoldering embers. CMBR is like those embers. It's a faint glow that fills up the whole universe, and scientists think of it as the leftovers from the Big Bang. It's pretty much everywhere and gives us a snapshot of what the universe was like shortly after the grand explosion. Redshift of galaxies. Next, let's talk about something called redshift. You know how a siren sounds different as an ambulance drives past you? That's because the sound waves are getting stretched. The same thing happens to light from galaxies as they move away from us. The light stretches, shifting to the red end of the spectrum. Imagine pulling a slinky. You stretch it, and the coils spread out. That's what's happening to light as the universe expands. Unanswered questions. But the Big Bang Theory isn't airtight. There are gaps. For example, it doesn't tell us what caused the Big Bang in the first place or what was happening before it. And if you're scratching your head about dark matter and dark energy, you're not alone. Scientists are too. We've got a pretty good idea of how the universe started, backed by some solid evidence. But like any good mystery, there are still some unanswered questions that keep scientists and us guessing. Are you enjoying this trip through the cosmos so far? If your mind is as blown as ours, make sure you hit that like button and subscribe for more mind-bending content. What was going on before the Big Bang? First, we need to wrap our heads around the idea that according to classical physics, time as we understand it and general relativity began with the Big Bang. If we were to trace time backwards, we would find the universe gets hotter and denser until we reach the infinitely hot and dense singularity. This was the very start of everything. But hold on to your hat, because we now wander into mind-bending territory where time starts to get a bit fuzzy. It is important to understand this singularity is a mathematical solution, but in reality, our understanding of time, based on general relativity, ceases to be applicable. So, the very concept of a before the Big Bang becomes nonsensical, because time itself originates with the Big Bang. What is needed is a marriage between general relativity and quantum mechanics, but the challenge lies in the fact that both theories, as currently understood, provide conflicting descriptions at these extreme conditions. To help navigate our understanding of what came before the Big Bang, we have some speculative theories and models that offer some insight and make our heads spin. Quantum cosmology and the no-boundary proposal. Proposed by James Hurdle and Stephen Hawking, quantum cosmology makes the noble attempt to reconcile general relativity with quantum mechanics. The no-boundary proposal suggests if we apply the principles of quantum mechanics to the earliest moments of the universe, the concept of a singularity and a beginning of time might be removed. Instead of a singular starting point, the universe would have smoothly transitioned from a small, compact state to its current expanding state without an explicit beginning. The no-boundary aspect of this model suggests if you go back to the beginning, time becomes non-existent mathematically and transitions seamlessly into space. The universe, therefore, does not have a starting point in time, but what we know of the Big Bang was simply a point in a broad, timeless cosmic landscape. In simple terms, the idea of a singularity is replaced with a quantum state. The cyclic model. Imagine the universe as a heartbeat. Imagine the universe like a heartbeat. It's not just one thump, the Big Bang, and then nothing. Instead, the universe might expand and contract in cycles, just like a beating heart. Think of a universe that breathes in and out over eons. So we would currently be in the 14 billion year-long breathing out phase. We also have some models within cyclic cosmology that offer ideas on the mechanics of these expansion and contraction phases. Some scientists believe the universe expands and contracts in endless cycles, while others, drawing from string theory, think our universe might collide with others in higher dimensions, sparking new beginnings. Sir Roger Penrose proposed that our universe's expansive end seamlessly transitions into the next, cycle's beginning. Another perspective, based on quantum theories, suggests our universe might bounce back from contraction to expansion. And then there's the intriguing idea of bubble universes, forming in an ever-expanding cosmic backdrop. One of the challenges of these cyclic or pre-Big Bang models is finding empirical evidence to support them. Some researchers hope that clues might be found in the pattern of cosmic microwave background radiation or in the distribution of galaxies in the universe. If there were previous cosmic cycles, they might have left imprints or echoes that we could potentially detect. Multiverse theory. A bubble bath of universes. From heartbeats to bubble baths. Imagine an endless ocean with bubbles popping up here and there. Each bubble is its own universe, and guess what? We exist in one of those bubbles right now. This idea, called the multiverse theory, says there might be countless other universes besides our own. As we dig deeper into the fundamental nature of our universe, several questions arise, such as, why do the constants of nature, like the gravitational constant or the charge of an electron, have the values they do? Why do the conditions of our universe seem fine-tuned to support complex structures? A multiverse provides one possible answer to these questions, where each universe has its own properties, and ours just happens to give rise to the reality we see around us. In the vast realm of cosmology, the multiverse idea provides an intriguing backdrop to the origin of our universe. Within this framework, our Big Bang is not necessarily the beginning of everything, but merely the start of our specific universe's chapter. Picture a setting where eternal inflation is the norm. The cosmos is always expanding somewhere, and our Big Bang is just a localized event in this ever-inflating tapestry. String theory offers another layer, suggesting our universe might be a brain floating in higher dimensional space, with Big Bang-like events triggered by collisions between these brains. In this expansive multiverse perspective, our linear notion of before and after might not even apply universally, challenging our very understanding of the universe's origin. So, if we are still speculating about what came before the universe, are we any more certain about what the universe is expanding into? The expanding universe. Expanding into what? Okay, so we know the universe is expanding, and this expansion is getting faster. How do we know this, you may ask? When we look at distant stars and galaxies, their light often appears stretched out, making them look redder, a phenomenon called redshift, similar to how a moving siren sounds different as it approaches or recedes from us. This redshift tells us those celestial bodies are moving away, and intriguingly, the farther they are, the faster they're receding, hinting at a universe that's expanding in all directions. Adding to this story is the cosmic microwave background radiation, a faint echo of the Big Bang, which paints a portrait of a very young universe and offers insights into its early expansion. Astronomers further refine their understanding using a toolkit of measurement techniques like observing specific stars and supernovae, piecing together a cosmic distance ladder that helps pinpoint just how fast the universe is spreading out. This accelerated expansion is attributed to the elusive and enigmatic dark energy, which operates as a counter to gravitational forces. Okay, so it has to be expanding into something, right? Hold on to your hats once again as we try to understand this. Imagine the universe as the surface of a balloon. As the balloon inflates, its surface stretches and expands. But if you were a creature living on that surface, you wouldn't see any outside it's expanding into. Similarly, if the universe is curved onto itself, it could expand without necessarily occupying some external space. Alternatively, considering the vastness of space, the idea of an infinite universe means it could be expanding without any reference to an outside. It's like an endless landscape stretching in all directions. Delving deeper into the realm of theoretical physics, some propositions, including the intriguing string theory, suggest the existence of more than the three spatial dimensions we're familiar with. In this view, our universe might be akin to a three-dimensional sheet or brain that exists within a space of higher dimensions. And as it expands, it does so within these larger dimensional realms. This then forces our inquisitive mind to ask the obvious question: if the universe is not expanding into anything, then it must mean nothing exists outside the universe? But how do we define the cosmological concept of this nothing? Is nothing something? Now, the idea of the universe not expanding into anything might make you scratch your head. We often think of expansion as something taking up more room in a pre-existing space. But here, it's not about filling a void or expanding into a nothingness. It's simply that the fabric of space itself is stretching. Think about it this way. If you were an ant walking on the surface of that inflating balloon we mentioned earlier, you'd just notice other points on the balloon's surface moving away from you. You wouldn't be aware of the larger space the balloon is filling. You'd only notice the balloon's surface itself expanding. Similarly, in our universe, galaxies are moving apart because space-time is stretching, not because they're filling a cosmic void. In our everyday conversations and understandings, nothing usually refers to the absence of something tangible or detectable. For instance, when we open an empty box, we say there's nothing inside. However, when we venture into the realms of cosmology and quantum mechanics, our intuitive idea of nothing undergoes a dramatic transformation. In these domains, even the seemingly empty vacuum of space isn't devoid of activity. Within this vacuum, due to the quirks of quantum mechanics, tiny particles and their corresponding antiparticles can spontaneously appear and then annihilate in fleeting moments. This phenomenon leads to a constantly bubbling quantum foam at extremely small scales, challenging our traditional understanding of a pure void. Then there's the philosophical perspective, which dives deep into abstract thought and contemplation. Philosophers have long grappled with the very notion of nothingness. It's a debate that touches the foundations of existence, logic, and understanding. Can there ever be a state or concept that truly embodies absolute non-existence? And if so, can we, with our language and thought processes, genuinely grasp or articulate this absolute nothing? This age-old philosophical question underscores the depth and complexity of a term that, on the surface, seems so straightforward. Nothing in space is kind of, well, different. When we say nothing in everyday life, we mean the absence of something, like no people in a room or no cookies in a jar. This is a relative concept based on our immediate perception and understanding. But in the realm of cosmology, nothing is a trickier concept. In this domain, even the seemingly empty vacuum of space isn't devoid of activity. Within this vacuum, due to the quirks of quantum mechanics, tiny particles and their corresponding antiparticles can spontaneously appear and then annihilate in fleeting moments. This phenomenon leads to a constantly bubbling quantum foam at extremely small scales, challenging our traditional understanding of a pure void. And as is often the case, where physics stops, philosophy enters to chart an outline of a road into the unknown. Like the number 0 in math. 0 is not just an absence, it has meaning because it's relative to other numbers. In the same way, nothing, in a cosmic sense, only has meaning when compared to something. So while we may talk about empty space, the emptiness isn't so straightforward. It's a sort of relative nothingness. Philosophers have long grappled with the very notion of nothingness. It's a debate that touches the foundations of existence, logic, and understanding. Can there ever be a state or concept that truly embodies absolute non-existence? And if so, can we, with our language and thought processes, genuinely grasp or articulate this absolute nothing? This age-old philosophical question underscores the depth and complexity of a term that, on the surface, seems so straightforward. So, the next time you look up at the night sky and think it's mostly empty, remember, it's a stage where countless tiny dramas are playing out in the blink of an eye.